Okay, so we covered like the most important parts of the C code as to how it looks like in the memory. And what we now wanted to do was cover the critical concepts that like every embedded engineer should know. And those are about like struct and union, volatile and const keywords, and then bit manipulation and pointers. So some we wanted to give some tips and some hints as to what you should not miss when dealing with these concepts. All right. So what we'll then do is split the discussion in four different lectures, and let's kind of start off covering struct and union. Go ahead.
Okay. So, well, basically, here what we are planning to do is sort of make you aware of what all important aspects you need to be aware of all these topics. And secondly, what all people look for in an interview or in a different
Technical
setting.
discussion.
Yeah, some technical discussion setting where they expect some knowledge or some awareness of these topics, and that is what we are here to provide. All right. So structure and versus union. So if I were to sort of define structure, I would basically use this one liner where the structure is equal to sum of its part, precisely equal to sum of its part, and we'll sort of shed more light on what do we mean by this. But this is for the structure, and for the union, it represents the max of its part. Like, if again, we'll explain this in a detail, but this is how I have sort of remembered what a structure means and what a union means.
Right. I have an interesting analogy for union, the way I remember it. And well, let's see. Well, I'll explain once we get there. Go ahead. So
Okay.
struct.
So slight motivation for structures and unions. So for structures, let's say you want to club the related data together in some construct which you can identify as a whole. So for example, let's say you are dealing with a Ethernet packet, right? And it has like multiple fields to it.
Hmm.
MAC
Some
address for
header.
source, yeah, some
Yeah.
header, MAC address for receiver, then the data, then the CRC and all of that. But you know for sure that this is sort of all belonging to one Ethernet packet, right? And you want to somehow club it all together in some construct, and we'll see how struct helps there. And
Right.
the reason for that is, if you have combined everything into one structure, then you can play around with the arrays of that structure very easily. So for example, you have hundreds of Ethernet frames, then you
Right.
don't need to sort of uh, manipulate the destination field of each of these frames or each of these packets differently. You have a nice structure which can intuitively help you to just initialize and move stuff around and play with it.
Right. And if I just want to kind of add a layer of imagination on top of that. So let's say we were just dealing with Ethernet packet as a buffer. Right? So what would happen is there are some bytes which have, let's say, the header. Then there are some bytes which will have, let's say, the CRC. Right? Then there is like the actual payload. So what we should think of is, okay, if we want to prepare this buffer as an Ethernet packet, we would need to go and manipulate each of these bytes, and
Hmm.
that is very difficult because starting of the buffer, you have to keep track of how many bytes to populate,
Hmm.
how many bytes to skip, where is the CRC from the base, and so on and so forth.
Hmm.
So that math needs to be done by the programmer. Instead, if we use a struct, what will end up happening is we can name these entities, the header, and there can be entities within the header also, and we can then access them using the names of those
Hmm.
entities.
Hmm.
So when we say, let's say this was ETH,
Hmm.
and ETH had a header, so that
Hmm.
would mean that this region needs to be
Yeah.
there.
Yeah.
If it had ETH dot, and dot is the way to kind of access an element within a struct. And whether to use dot or the arrow depends on whether you are using struct as a variable or you have a pointer that is pointing to a struct and then you want to dereference. So, the dot and arrow depends on pointer or not a pointer. Okay, so if we said then eth.crc, we would automatically be
Hmm.
populating this much region. And this is how, struct makes life easy.
Easy. And I can clearly see this is much more elegant and like ultimately zero error prone. If you are
Yeah.
using the first approach where you are keeping the track of the bytes
Hmm.
yourself, like ETH's fifth byte has CRC starting,
Very
right?
difficult.
Then very difficult to treat.
Yeah.
And also, let's say if you want to add, let's say, one more field after header, then all your CRC offsets are now going to change in the code,
Yes,
right?
and
So
you
it's
you have to rewrite your
yes,
code, rewrite the math. So struct just saves all of that
saves
effort
all of
for
them.
us.
And this is why we have, like, we, at least I and Piyush, consider it is a very important topic,
Yes.
because it might not sound like, hey, it's a big deal, but if you see, from programmer's perspective, when start your embedded career journey, you would see struct being used everywhere,
Left,
left
right,
and
and center. Yeah.
yeah.
In fact, at this point, we should let people know that a peripheral, again, this is something we alluded to in one of the
Hmm.
earlier lectures, but a, a struct is very useful to essentially create a mapping for the peripheral registers. So, a peripheral, like let's say UART.
Hmm.
So, it has, let's say, some 10 registers. So, what you can do is you can have unsigned int and the register name. So
Hmm.
TX or data, line status,
Hmm.
whatnot. And what you can do is you can pack all of that under the name UART struct.
Hmm.
And now further down, what can happen is what usually happens is you have this a
Hmm.
pointer which is of the type UART structure, and then we say, hey, it's actually pointing to, let's say, hex 1000. And hex 1000 happens to be the actual memory location
Hmm.
where the UART registers are mapped.
Hmm.
So all of a sudden, what will happen now is when we do UART arrow ls, we are
Hmm.
reaching the second register, which is right here, which is the line status,
Line status.
something like that, right? So in the embedded context, pointers and structures together kind of give us power over controlling the peripherals. And not only are they used for data manipulation
Hmm.
here, structured data manipulation, but also for peripheral
Yeah.
manipulation.
Yeah. And it,
Okay,
it
so
abstracts out, the addresses quite well from the
yes,
programming.
yes,
So if, let's say, for some reason you had address change from 1000 to, let's say,
2000.
2000, then this would just be, a change in one of the header files. That's it.
Yes,
Your
that's
code
correct.
remains as it is.
Right.
So
So yeah,
cool.
that's I think that's pretty much the story about
Of the
struct.
structure.
And let's talk about the padding and the non-padding
Right.
case. So let's say we have a struct, I don't know, x, y,
Hmm.
z. So this is how the definition usually is. And then let's say we have an int a,
Hmm.
character b, and a float
Hmm.
c. So if we are to kind of imagine as to how much space or what the layout would be. So there should be two imaginations. Well, one is that there would be definitely the first element would be an int that would occupy like 4 bytes, and 4 or 2 bytes, because int, depending on what machine you are
Hmm.
on, it's either 2 bytes or 4 bytes. We'll assume it to be four. So int occupies, what did I just do? Oh, okay. Int A. So int occupies 4 bytes. After that, there is a character of 1 byte. So now comes the case of whether there is padding or whether there is not padding. If there is padding, then 4 bytes will be allocated, out of which 1 byte, and I don't recall whether it is the byte on this side or the byte on the further
Hmm.
down, but 1 byte will be for B because character is 1 byte. So we have 4 for int A, and character B is 1 byte. So there would be a hole here of 3 bytes.
Hmm.
And then after that, there would be a float C,
Hmm.
which is 4 bytes. So if the compiler ends up doing or adding padding bytes, then the size of the structure would be 12,
Yeah.
right? And this is where Mohammed's statement about sum of the parts
Hmm.
kicks in. So the size of the structure is sum of its parts. It's round up to 12 here
Hmm.
because of the padding bytes. And the question is, why would the compiler add in padding bytes? Well, the answer to that is access to aligned bytes, so word
Hmm.
aligned bytes, is faster on
Yeah.
machines, on 32 and 64-bit machines. So the compiler, for the purposes of faster access to memory, ends up adding the padding bytes. But a good answer is, let's say we were to ask the compiler to do something called packed. So there
Hmm.
is like at least in GCC, there is a compiler attribute saying, hey, do not add padding bytes. Instead, what you do is just pack everything together. And if it packs everything together, then the size would be 4 bytes for A, 1 byte for B, so one here, and then 4 bytes for the float. And in total, this will come down to 7.
7. Yeah.
Now, another thing to remember is, let's say instead of A, B, C as character, we also had another character, D here.
Hmm.
Even then, in the what is a non-packed
Padding.
case,
Not packed case. Yeah.
there would be padding of only 2 bytes,
Hmm.
and B and D would actually have 2 bytes here. They will be allocated 2 bytes here, and the entire size would still be 12.
12.
So only after the let's say if we had two more characters here, E and well F, then all these 4 bytes would be consumed. There would be no padding bytes, but that is how it works.
Hmm.
It kind of only adds padding if we can achieve um, 4 byte address alignment.
Yeah.
Otherwise,
Yeah.
it wouldn't add. Cool. And people can do different experiments to check this out. But
Hmm.
this is something to remember
Right.
depending
And
on
this is
padding or
a,
not
I think
padding.
this is a very good question which can be asked from the
Right.
standpoint that they might want to probe you as to if you are aware of padding and how does that work. And
Right. How
also this
memory
word
layout
alignment.
works.
Yeah, the word alignment thing, right? So one more thing to add on the second case where, the structure is packed. Here, the compiler has to be fully aware of where it has placed what, and
Hmm.
while generating, or while, let's say you are referencing float, which was the last one, it has to make sure that it doesn't access, or rather doesn't uh, generate an unaligned memory transaction. So it will be very fully aware, and it
Hmm.
might, if you look at the disassembly we showed you in the earlier videos, how can you, check the disassembly. If you are curious, you can maybe try it out, and if you check at the disassembly, you might see that the float is being fetched in multiple parts, just because
Hmm.
it cannot do an aligned access right
Aligned
there.
access. Right. 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 Cool. So that is about the struct. Now
Hmm.
let's talk about the union.
Yeah.
Well, uh, one of the cases for union, just again,
Hmm.
some food for thought,
Hmm.
is, let's say you have a buffer, and there are, like, the size of the
Hmm.
buffer can vary, but depending on, let's say, for example, the first byte in that buffer, you figure out what the length or type of that buffer.
Hmm. Hmm.
Typically, do you want to give an example of this?
Uh,
The
That's
Ethernet, TCP,
Ethernet,
and
maybe. Yeah, yeah. Let's extend that. So let's go to the application layer. We have, like, different protocols,
hmm,
and depending on the port on which the data is received, that same
hmm,
datagram coming from the lower layers can be interpreted either as an HTTP frame, or an SMTP frame, or an FTP frame, or whatnot, right?
right,
But then the data per frame will also vary depending on what protocol it is. But let's say it comes with the port number, and I think it naturally fits your argument. Like, we read the port number and decide what protocol this frame belongs to, basically.
right. And let's say because we know what the max buffer
Hmm.
size is going to be like
Right.
the lengthiest
Hmm.
packet, so to speak. Let's say if it happens to be just, I mean, I know nothing about Ethernet. By the way, is there any background noise from my
Just
side?
a very faint one, but I think
Ah,
it's.
okay, fair, fair. So let's say the max packet size that we can have is 1024.
Hmm.
And then what we do is to deal with this packet, we have a struct which spawns or whose size is 1024.
Hmm.
And then let's say there is another one which is 512, for
Hmm.
example. Right? So we have another struct which has 512. Now, what we want to do is depending on the first byte
Hmm.
here, we want to figure out or interpret the data as one of the two structs.
Right.
So what we can then do is club these two structs together in a union. And then what we can then do is say, hey, check the first byte. And then depending on what that first byte is, for example, interpret these bytes as one of the structs. Now, again, this was, I think, too loaded. So we'll take a simple example of, let's say, the buffer is maximum 4 bytes, or let's make it 5 bytes. Interesting, right? 5 bytes. So one to check, and then interpret what all is going on. So what we can have is we can say we have a struct with character which is conveying the type, and then within that we can have union,
Hmm.
and that union can internally then have struct,
Hmm.
or well, let's not do that. Let's say the it has character data, data underscore c, or it has uh, int data underscore I, and it has float data underscore float. Right? So 4 bytes here and 1 byte here. So this entire structure has this field as type. So it will check, and if the value is 1, 2, or 3, what it can do is it can then choose, and we can say union data. It can then choose to interpret these 4 bytes as if it was data C, or it was data I, or it was data F. Now, the interesting thing here is data C is just 1 byte, which is equivalent of the 512 argument I was making earlier. It could be 4 bytes, so all the 4 bytes are used, or it could be another 4 bytes but interpreted as if it was a float. So, what people should remember is in case of the union, which is what you were mentioning, it's the size is the max of the elements. So, this union has 3 elements within it: character, int, and float. The highest size happens to be that of float and int. And we could argue the highest size actually is float because int can be 2 bytes on systems.
Right. Right.
So the size of this union is the size of the element that covers or needs the maximum number of
Maximum.
bytes. And the way I like to think about it is like this. So a character is one, and int is, okay, let's say 2 bytes in this case, for example, right? So two, and then there is float, which is 4 bytes.
4 bytes.
So
Yeah.
what I tend to see them as is something like so, and a shadow being project, like
Cast.
light being, yeah. So light is coming from top, and the shadow it
And
casts is of the highest
highest.
or the maximum
Max element.
memory occupying element. So that is a tidbit that people should remember. Union max size element is the size of the union, and in case of struct, it's simply sum of the parts. And then be careful about the caveat about optimizations or efficient fetch from the memory, and the concept of padding as a result of that.
Right. Right.
Cool. So anything else that you would like to add to?
I think this concludes it nicely. Just while you were explaining that, it just struck me that unions were like the OG polymorphism concepts. Like you
Oh,
could
is it?
morph your
Yeah,
data
yeah, yeah.
into whatever meaning or interpretation you want through unions.
Oh, yes, yes, yes. Well, here's like an example that people can try maybe. Save, so have a union of this nature where you
Hmm.
have a character int and a float, and then let's say store the value of -1 in the int, and then read that back as a float, and see what the answer is, just for
Yeah.
fun. The
Hmm.
encoding and the interpretation
Hmm.
differs, but it would be fun as to, okay, set some bits, then read those
Interpret it
back.
as a different.
Exactly. Perfect. So this
Hmm.
is something we wanted folks to
And
be.
Piyush, I think we should also mention that if you are asked or you want to try and find the size of your structures and unions, the size of operator perfectly works. So
Right. So
just to tell you.
use the size of operator,
Yeah.
and then put your struct or union right here and do a printf on this,
Yes.
and the size will pop out. By the way,
Hmm.
all of these concepts on C are very heavily discussed in the C language course. So if you're interested, you can also take that, and it will go into a lot of details at the processor and the system level. Okay, perfect. Anything else that we want to add to the
Hmm.
structs and unions?
I think I'm good. This is pretty much what I wanted to discuss here.
Okay, perfect. So let's conclude this lecture, and then as part of the next one, let's move on to discussing what were the other topics.
I
Uh,
think volatile
Volatile
and
and const.
yeah.
Const. Perfect. Okay, so let's conclude this, and we'll see you guys in the next one.